start?
More people will join in, I think.
But
I think we can start.
okay, cool. Let me share my screen.
Mhm.
Hey Arthur, are you still putting the code out on your site?
Yeah, gradually I think I have code for this chapter, but it's not like completely covered in Julia. I have some, so for this mountain car example, I've switched to Python to use OpenAI Gym environment.
Oh, I see.
But I will also uh, make a version in Julia so that there are like alternative environments, but I haven't yet decided if I want to go. There is like a Julia uh, kind of implementation of OpenAI Gym, and there is another another Julia environment which I think Andrea posted a link to the repo containing it a while before, and
I'll have to look for that.
yeah,
It's
I
interesting.
will probably go with that the later one
Okay.
and see how it goes. But yes, I think I haven't uploaded the Python notebook, or maybe the latest version, but I will do today. And I will maybe today briefly, uh, if you guys, I don't know if you are familiar with Gym and all the stuff you need to like run this simple mountain car environment. Maybe I will introduce it briefly today as we go through the algorithms related to
Oh, that'd be
like,
nice. Yeah, I have not
right.
used it before.
Okay, it's really simple. So we will see it as we discuss Sarsa Lambda. So last week I think we finished the like TD learning with eligibility traces, and basically that covers value function evaluation, or yeah, so the value function evaluation. And this week we will discuss uh, eligibility traces for control tasks. So uh, we will see that all the algorithms we learned for control uh, as before uh, will have their like variant using eligibility traces, and that is kind of more computationally efficient because of using this forward view uh, approach. And the modification we need to do to obtain Sarsa Lambda, uh, like from regular Sarsa and TD Lambda, are quite straightforward. So as you might remember, in Sarsa, we have this uh, like our target update is obtained by using the state and action pair, like a value for state action pair at the current time step, and the values for state action pair for the next time step. And by subtract, like by adding that and subtracting a reference, we get this update. So it would be this term here in equation 1215. So that's basically adaptation of Sarsa update rule for the weights in our case, so for the function approximation, and the modification that we need to do to obtain the like n-step returns is the same as presented in chapter 10. So we have this discounted sum of the rewards up to step t plus n, and the discounted q value for the final like t plus n state action pair, right? And so that is what we are using to get Sarsa Lambda. So as the same way as with TD Lambda, the Lambda return is defined like as this weighted sum of all the n-step returns, right? So we just take all the available n-step returns, sum it according to this exponentially decaying lambda weighting, and that gives us the lambda return for current time step. And that is what we are gonna use to construct Sarsa Lambda algorithm. And the update rules are given here. Those are basically very similar to the TD update that we discussed before. Just we switch from using the v hat to q hat, which also takes into account the action. And the update of the eligibility trace, basically it also remains the same, but we switch to using the gradient of q function. And here is a backup diagram for Sarsa Lambda. It's also, again, very similar to that of TD Lambda, and the sum of these weights from 1 minus lambda up to like lambda to the power t minus capital T, which is termination time, minus t minus 1. So this all weights summed up give us 1. So by adding this 1 minus lambda scaling, we make sure that we have a total sum of 1 for all these weights, and that's like the idea of lambda return. And now I think this is a very useful picture for understanding the impact of or the mechanics of lambda versions of the algorithms. So here we, the leftmost picture shows us the path that we taken to reach the goal state. Then we can see, and I think we saw this before, that one-step Sarsa would only update the state that preceded the terminal state here. And basically to propagate this update to the other state, we need more iterations. And by switching to, say, 10-step Sarsa, we will propagate the observed reward update associated with the observed reward up to 10 steps preceding the goal state. And as you can see, for Sarsa Lambda, we are kind of propagating this update backward all the way to the very very beginning of our path that led to the terminal state. And this decay is given by the lambda. So the higher, basically the higher value for lambda, the less decay we will observe, or lower value for lambda will produce quicker decay. And as you might remember that basically setting lambda to 0 will result in like one step learning, and setting lambda to 1 will be equivalent to Monte Carlo update, or similar to Monte Carlo update. So we will just take into account all like the total return rather than n-step returns. So yeah, and but what is going on like computationally in case of Sarsa Lambda, during as we traverse this path, we will accumulate this eligibility trace, or rather like compute this eligibility trace, and the update will be done at each time step, and but this update at the terminal step, for instance, will affect all the preceding states according to the eligibility traces we have associated with the path. So, right. Hopefully that makes sense. And here is the Sarsa Lambda algorithm. We can briefly walk through it. So this particular presented algorithm is relevant for linear function approximation using the tile coding. So here this phi function is a function that produces a sparse feature vector corresponding to the tile coding we have for this state action pair. So that would be basically the set of indices of active features here, right? And we have some policy that we using to act, and some hyperparameters for this algorithm, namely learning rate alpha, trace decay rate lambda, epsilon for the exploration in as usual, and we have two parameter vectors here. We need to initialize the weight vector W and eligibility traces vector Z. And during the algorithm, we start from some state. We act according to our strategy pi, and we starting with 0 vector for eligibility trace. We proceed through the episode. We take the action according to our strategy. Then we so this part of the algorithm is basically the same as computing this TD error, right? But here it's just shown to be done incrementally in a loop. And there are different ways of doing it. So not different ways of doing it, but different ways to like compute the eligibility trace associated with this path. So we compute the corresponding delta, and also we update the eligibility trace by adding or setting to 1 the value for z for that particular index. So here, just to recap, the dimensionality d of all these vectors is kind of determined by the feature space we have. So for example, we kind of here, if we are using tile coding, we can have up to some number d of distinct tiles, each of which has its weight, a corresponding weight, and also each weight has corresponding entry in the eligibility trace, which will like show us how much this weight should be updated or is like eligible for getting the reward we observe during this time step. So, and therefore, how much should we move this weight? Like how much did that particular weight contributed to the particular observed delta, or delta is TD error essentially. Okay, and we will see this in the code, so that should make sense, right? So here, this is another loop here that basically here we add as before, we add this gamma w sub I, which is equivalent to adding the Q function corresponding to the next state. Yeah, and finally we update the weight, and we update the eligibility trace, decaying it by lambda and gamma factor. Okay, and here we can inspect the results of like Sarsa Lambda applied to mountain car example as compared to n-step Sarsa. And you can see that, so this is the result for first 50 episodes. And you can observe that early learning for Sarsa Lambda is quite good compared to n-step Sarsa. And why? And as you remember, we didn't see any difference when comparing TD Lambda with n-step TD algorithm. But here we observe this improvement. And why is that? And essentially that is because we in n-step learning algorithm, we delay the update of the weights to like n steps forward. But with the eligibility traces, we at each time step, we kind of update our weights according to the latest observation. And when dealing like with value function evaluation, this did not has any impact. But when dealing with control, this has this quite sizable impact on the early learning, because like we basically update our weights, and therefore we update our policy as soon as we get like a new information. And that is not the case with n-step Sarsa. There we kind of delay the update n-step into the future. So that at least is my understanding why this difference is observed. All right. So that is this nice property of Sarsa Lambda compared to n-step Sarsa. And here we can compare different kinds of Sarsa algorithms. So one can see that the accumulating traces perform worse in this case. And essentially, you can see that Sarsa Lambda with accumulating traces is better at low learning rates, but it doesn't work with higher learning rates. And Sarsa Lambda with replacing traces like performs worse, but it operates on a wide range of learning rates. And the best performing algorithm is true online Sarsa Lambda. And here one can see the algorithm for true online Sarsa Lambda. But as you remember, the for this true online Lambda algorithms, we need to find the analytic form for these updates, and it will vary depending on the function approximation we use. And basically, this makes it only easily applicable to the linear function approximation case, but not for complex neural networks, obviously. So it would be probably infeasible to find the analog for an algorithm that relies on a large neural network. But like for this linear function approximation case, it is definitely the best performing algorithms from those. All right, so to make it more clear, let's have a look at the implementation. So let me just probably make this full. Oh, sorry, this full screen. So can you see the notebook?
Yes.
All right. So what we do here, first thing to note, I am using this tiles function implementation from Rich Sutton's site. So they have a reference implementation of tile coding. Basically, let's quickly check out what it does. So we have to define this basically size of our tile coding space. And then we can use this tiles function to produce 8 tilings. And here, these tilings will should be similar for states that are close together, but different for states that are far apart. And here you can see I'm printing a bunch of tile indices corresponding to different states. And you can see as we vary the state. So for 2 close states, so this state is like represented by 2 numbers. So here it is 3.6 and 7.2 and 3.7, 7.2. And the tiles are almost identical. So only one tile had changed. One tile index has changed between these 2 states. But if we move further away from this state, we observe a completely different set of tiles representing to this state. Okay, and for the...
What does this signify? This change in a number, is it random or?
So essentially, the numbers are just assigned sequentially. So starting from 0 and up to 1024, excluding, I guess. Yeah, and basically this numbers signify the tiles, and you can think of it as hashing each state is hashed to 8 numbers. And the way this hashing function works is that it hashes the states that are close together to the same tiles, but the states that are further apart are hashed to completely different tiles. And here, if you inspect these numbers, once I moved one away, like in a state space, basically Euclidean state space, one away from the original state. So here we are at 3.6, and here we are at 4.8 in one dimension of state space. The styles are changed completely. And once we take this intermediate state between the third and the first here, we can observe that some tiles overlap. And maybe we can quickly go back to the place where tile coding was introduced. Let me just quickly find it to make sure that everything is clear here. So, all right, so this is the way tile coding works. Basically, we can imagine it as like we have this continuous state space in 2D, and then we kind of cover this state space with tiles, and each point will be covered by some number of tiles everywhere in this case. So by calling this tiles function, we want to produce 8 indices of corresponding tiles. And each tile is like a binary feature. So if the state is inside the tile, it will be 1 for the feature, and if not, it will be 0. And you can think of it as a way to produce a simple way to produce this sparse features.
Yep. So the overlapping those tile points, these fields will cause a point to be represented. So after this 4 tiles, the 4 sets of 8 tiles that we have created, those points might be referenced by a particular number, which is highlighted in the state space by the representation of the 4 set of 8 tiles, right?
Yeah, and that results in generalization. And
Yep.
here is this kind of how we can see this generalization patterns here, that the close points will have a lot of tiles in common, but the points that are further away one from each other, they have a set of completely different tiles, and therefore to compute the corresponding value function, we will use a different set of weights. So essentially, that's a quite simple idea, but the implementation is done here using this hashing function that produces the desired number of tile indices, and here we use 8 tiles. Okay, and to make it work correctly, we need to scale our state space to be between 0 and 10, so that that's what we do. That is specific to this particular implementation. Yeah, and you can find this. I will post maybe a link to it. You can find this on Incomplete Ideas website. Okay, then we have this mountain car environment, and just a brief demo of what it does. You can see, yeah, maybe let me run it a bit slower. So here what I do, I just apply the action that moving this cart towards the goal. But as you can see, it basically, we don't have enough power to just go directly to the goal. So we need to come up with some smart strategy to go up the hill. And the gym environment, so gym is just a framework that wraps this different kinds of environments. And there are these simple classical environments like pole balancing and, for instance, this mountain car. But also there are a bunch of more advanced environments, like, for example, those relying on this Mojoko, or I'm not sure how it's pronounced correctly, but this physics engine, and that can be applied to robotics tasks. And what Gym provides, provides us a unified interface to all those environments. And by calling the environment step function and feeding it an action, a valid action, we get this observation, which would be our state, the reward, the done binary variable that or Boolean variable that corresponds to whether the episode is finished, and also info variables that might provide something for us, but we don't use this in that case. So essentially, that's very similar to those kinds of environments that I've been using in my like manually implemented environments for the previous problems we dealt with. So nothing too special about these gym environments, but it allows us to access a wide range of prepared, pre-made environments, and that's really nice. So we have the associated observation space and the action space. And in this case, we have only 3 discrete actions, like go backward, go forward, or do nothing for this task. Okay, so our value, so in this case, our value function would be just apply the tile coding to the state action pair, and then multiply we do like dot product of weights vector by this sparse feature vector. So it can be done more efficiently by just indexing to the weight vector and summing up all the weights with the corresponding indices. So that's essentially the same as like doing dot product of these 2 vectors, right? So that's our action value function, Q function. And now, like for baseline, I have this simple one-step Sarsa algorithm here. And yeah, we can essentially run a bunch of episodes, see that it works. And yeah, let me just quickly run one run to you can see as the training progresses, the number of steps per episode decreases, and eventually we will end up with something closer to 100 steps per episode. And then we can run this policy we obtained in the environment. And yeah, as you can see, maybe again, I should make it a bit slower so that you can see that it goes backward and forward and finally reaches the goal. And depending on the starting state, it can be kind of quicker. You see that here we had 91 time step, while in the previous run we had like 171 time steps. But overall, that is you can see that this non-trivial strategy of getting to the top of the hill is discovered by Sarsa algorithm. And then we can apply n-step Sarsa to the same task. And yeah, here I have some result comparing 1-step and 4-step Sarsa. You can see that 4-step Sarsa performs a bit better early on in training. And now to the Sarsa Lambda algorithm. So what we do here essentially, we have one thing to note here is that we have a bunch of hyperparameters for this algorithm. So we have a lambda, we have a learning rate, we have this decay parameter gamma, we have exploration rate epsilon, and we also can use replacing traces or accumulating traces. And yeah, so that's something you can use. And basically difference between replacing traces and accumulating traces would be in a way you update this z vector. So for replacing traces, we set the the values in z corresponding to this index to 1. But in the accumulating traces, we increment the values in z by 1. And otherwise, it's very similar to the TD, or not otherwise. So in general, it's very similar to the TD learning algorithm we discussed last week. And it produces some okay-ish results. But here you can see the comparison of the learning curves for Sarsa Lambda and true online Sarsa Lambda. And you can see that this green line that corresponds to true online Sarsa Lambda is just much better early on. But I guess here I might have some error in the replacing traces implementation, because or maybe that's because of low learning rate I was using here. So yeah, so there is this learning rate parameter, and it might be different for different algorithms. So that here I used same learning rate for all 3 algorithms, but by varying the learning rate, you can get better performance from some of them, but other algorithms diverge when you use a high learning rate. So that can be found, the detailed let me find this. The details can be found in this table here. You can see that, for example, Sarsa with replacing traces performs poorly with low learning rates, but on higher learning rates, it kind of catches up. But the Sarsa with accumulating traces performs a bit like or reasonably better with this low learning rates, but it fails to converge with the higher learning rates. And we can just try it out by setting alpha here, say to even 0.5 in the paper, and one should suspect that yeah, you can see we just have a numeric instability, so the training diverges, and now for each episode takes the maximum number of steps I've set here. So yeah, we basically failed in this case. But by using a lower learning rate of say 0.1 here, we will observe the progress. But also it is kind of slow, or a bit slower than that we would like. Okay, so that's essentially the basics. So we mapped the approach we developed for TD Lambda to the control task and produced Sarsa Lambda and true online Sarsa Lambda like for the control. Now let's proceed with introducing some ideas that makes this algorithm even more general. So first thing we can do, we can essentially think about this. So so far we considered lambda and gamma to be constants, but what we can do, we can we can think of lambda and gamma as of functions. So lambda would be function of state and action, and for each state action pair, we can have different this trace decay parameter. And the same with discount rate. For each state, we can have different discount rates. And in this case, the total return will be like this sum from k equals t to infinity of the rewards multiplied by the corresponding gamma. So now we have this index for gamma, and for at each time step we can have different values for gamma. And to make sure that this sum is finite, we need this product to be 0, which means gamma should be less than 1. So probably to like really make sure that this product is 0 and this sum converges, we need to exclude the 1 from this function here. But yeah, that's for continuing task. Or we can have like another way to make sure that this product is always 0. If we have like a terminal state, we can make this gamma function such that gamma of terminal state would be 0, and then we will always eventually multiply this product of all gammas by 0, which will kind of reset the accumulation, right? And so that makes sense. Once we reached the terminal state, the or rewards after that are not relevant to the to what we observed before. So we start a next episode and we accumulate a new reward starting from that time step. But in this way, we kind of formulated the episodic task and as a continuous task with this termination function, essentially. So the gamma can be viewed as a termination function. And we briefly discussed this idea that discounting is like a soft termination when we speak about the emphasis and derivation of it. So you might hopefully remember that intuition that by setting gamma, for example, to 0.9, it is kind of equivalent to saying like at each time step we are terminating with probability of 0.1, right? And by setting gamma to 0, we just say that in this state we terminate with probability 1. So, and you can see that we can kind of introduce this concept of pseudo-termination as well by making gamma a function. So like zeroing out this gamma will essentially be equivalent to terminating the episode. Or more precisely, terminating the propagation of propagation, the impact of the future rewards to the total return we gathered so far. All right, and now we can also define this lambda return using our new notion of lambda as a function of state and action as well. And in this case, we will have this recursive definition of lambda is modified as follows. So we will have 1 minus lambda of our value estimate for the next state plus lambda of the lambda return for the next state. So, and you can see that this is kind of a linear combination of these two values, right? So we take our function evaluated in the next step, and then we take the lambda return associated with the next state as well. And
so here discounted returns are taking as lambda, which is being replaced here by gamma.
No. So we still have, so those are kind of orthogonal concepts, but in the algorithm, they essentially, well, let me just switch back to the code quickly. And for example, here, what is this? So this is a Sarsa Lambda algorithm. And you can see that when updating the eligibility trace, for this simple Sarsa Lambda algorithm, at each step, we decay the eligibility trace by gamma times lambda. And the gamma came here because of discounting. So in this particular case, gamma is 1. So for this task, we used value 1 for gamma. So it has no impact on the algorithm, but we still have some lambda that is between 0 and 1, and therefore we decay the eligibility trace. So in a sense, there are like two kinds of decay we want to introduce. So gamma it remains as before, like we, and it is basically task dependent. So for different tasks, we might want different values for gamma, and that's basically kind of represents the dynamics of the environments in a way. For example, in some environments, the action at like can have some impact 1,000 time steps in the future, and in that case, to be able to learn that dependency, we need to set gamma to be like really close to 1. But if, for example, we can safely ignore values like, say, 10 steps to the future, then we can set gamma to be 0.9 and use it just fine. The lambda is like another concept which is like similar in mechanics, but here it is kind of introduced that in a way that we think of it as how much this current step contributed to the reward we observed some t steps into the future, right? And by setting gamma to be like closer to 1, we propagate this contribution further back, but by setting it, so the lambda is property of the learning algorithm, and gamma is property, or like is connected to the environment or like task definition we have. Yeah. All right, and but as you noticed that those two have very similar kind of algorithmic impact on the process. So, and they almost always appear together in the as a multiplier to some value. And here you can see that we can apply the same kind of modification to here we denote it as lambda return corresponding to the action, and here you can see the action value function used. And but the formula is again the same. We have this linear combination of our action value estimate and corresponding lambda return for the next state. So this is kind of recursive definition in terms of future lambda return, as well as current estimate. And again, to remind you, you can make the expected Sarsa variation of it by substituting the value corresponding to some particular action by the expected value of the state according to current policy. So with this V bar is just a weighted sum of action values for all possible actions weighted by the action probability. So for example, if we have 2 actions, one of which is 90% probable and another 10% probable, we will just take both action value function for both actions and sum it up by multiply it by this action probability. And we will use that as our, essentially as a part of our expected return rather than the sample we take. We use an expectation in expected Sarsa, and that makes it kind of off-policy algorithm. And now let's discuss different kinds of modifications that can be done to Sarsa to produce analogous off-policy algorithm. So first we discuss this off-policy traces with control variates. And you might remember that this was introduced in for tabular cases in chapter 7. And when we discussed the n-step bootstrapping, there were a bunch of variations of policy algorithms, and like the basic way to or one way to introduce of policy training to our like arsenal is to use the importance sampling. So we have this raw sub t, which is the ratio of probability of the action under target policy by the probability of action under behavioral policy. All right, so I believe this was discussed in details during our sessions for chapter 11, and there we saw that the using this importance weight in importance sampling introduces it allows us to evaluate like off policy, but it also introduces a higher variance to the process. So here let's see what do we do to obtain this to introduce the importance sampling into Lambda return. So here we take again a linear combination of this quantity. So here you can see that this is a Lambda return as defined in the previous section, multiplied by the importance sampling ratio, and then 1 minus importance sampling ratio multiplied by the we have for this state. And if when we have on policy data, rho will be always 1. So this one becomes like 1. So we can safely ignore rho here, and this becomes 0. So we will just take all of this component and 0 of this component. But when our policies do not match, then we have kind of a bit of difference here. And essentially what we can kind of think of it, that when the action we observed is more probable under target policies, then we upweight the experience and downweight our previous estimate. And otherwise, we will just upweight or downweight the experience, but upweight our like previous estimate to compensate for it. So that will make our target kind of better. So we will avoid setting this to 0, because as you remember, so that is what control variates help us with. So as you remember, if the action has 0 probability under target policy, then we will have rho equal to 0, and that will introduce like a lot of variance into our updates. But by using this control variates, we will compensate for those zeros in rho by kind of adding the proportion of our previous estimate we had. Right, so now we can define the TD error corresponding to the state. You can see here this TD super S, and that is just the TD error as we are used to see. And yeah, so then we can define a lambda return corresponding to this state in terms of like the value of current state. And you can see that this is approximation because actually we will have this W changing in time. And this approximation will become exact if the weight is constant. So if we remove this dependency, so if we don't update weight, then this will be exact. But otherwise, it is an approximation, and it just used to provide you some intuition of what do we have here, right? So we have this a sum of TD errors weighted by gamma times lambda times the importance sampling ratio. And yeah, so that would be kind of product of all the importance sampling ratios that we multiply this factor. And again, as you remember that if our target policy is not close to the behavioral policy, this can become kind of quite volatile and introduce a lot of variance into the learning. So, okay, let's proceed with this. We will have a new update rule for our learning algorithm. So this is a forward view update rule. You can see how can we update the to get the W sub t plus 1 from W sub t and new observation. And in this case, we can use this approximation for updating. And if our step is small, you can assume that this approximation is better than like so. So recall that this approximation is exact when we have a constant W. So if W changes just a tiny bit, then this approximation is quite good. But if we have a lot of variation in W across time step, it might become worse, I guess. So that's another nuance here. And again, one can demonstrate that the sum of updates would be equal to the sum of the like weighted TD errors. So you see this product weighted TD errors multiplied by gradient and importance sampling ratio, a lot of components here. But essentially what we have here is that, yeah, this would be again exact if the weights don't change, but it is an approximation if the weights change. All right, and we can also express the eligibility trace in a similar fashion. So here we have this eligibility trace update corresponding to the off-policy algorithm. So essentially, it is the same as before, but we also have this importance sampling ratio multiplier. So by expressing here, observing that this all product sum and the product it gives us or sum of products it gives us an value of z at the previous time step. So we get this nice recursive formula for updating z, so the eligibility trace. Okay, so that's kind of an introduction, and then we have all the same stuff for Q values. So again, this is this is essentially just the same as for state values, but this time we work with action values. And now we have like these two decisions that we can also produce the expectation form of it. So that would be like, instead of using a sample here, we can use an expectation. So this v bar is expectation for s sub t plus 1. So the sum over all actions. And as you can see in this case, when taking expectation, we get rid of one multiplication by important sampling ratio. So we still have the important sampling ratio for all the upcoming components, but we don't have this row here. But let's just roll back to it. So here we had row, but here we take the expectation, and therefore we do not need the important sampling ratio. So, that was like as we observed before with expected Sarsa, right? And with n-step expected Sarsa as well. And the update for Z is just the same again. And let's see. There are also a lot of variation of these algorithms that we might want to use. For example, so we have used this approximation here for getting the Lambda return, but there is kind of exact form of it, and it's only mentioned in this chapter. So to find the details on it, we would need to check this paper by Sutton and also Van Hasselt, who's like a lecturer in that deep learning course by DeepMind. So, or reinforcement learning course by DeepMind. So a lot of familiar people here. And yeah, so there is this provisional TD lambda algorithm and a PQ lambda algorithm, but no details for that here. So that's kind of probably a bit more advanced stuff. All right, so that's one way to produce the off-policy learning algorithm for the eligibility trace, using the eligibility traces. But also recall that the Q-learning algorithm is also off-policy algorithm, and we avoid using the important sampling with Q-learning because we take we always take a maximum of Q value for our update rather than taking a sample. And a maximum does not depend on the behavioral strategy. We can determine the maximum according to our target strategy, right? And therefore we do not need the important sampling ratio. So the question is, can we produce the equivalent for that? For eligibility traces equivalent for that, and that is what's called Watkins Q lambda. And so the modification done here is as follows. The eligibility trace is decays as usual, as long as greedy action was taken. So as long as the greedy action was taken, so we can rephrase it, as long as we act according to our we select the best action, then we decay the traces as usual, but we set traces to 0 if we take non-greedy action. So once we deviate from greedy strategy, we just zero out the trace, and that gives us this basic Watkins Q Lambda algorithm. And here is a backup diagram for that, and you can see that it progresses up to the first, like up to termination or up to first non-greedy action. So in both cases, we will just use we will change this decay of the eligibility trace. And all right, so and as you can see that for first non-greedy action, we just take this I believe what is expectation over all actions, right? So that's what.
So, yep, will be a Monte Carlo update, if I'm not wrong.
All right. So that's okay. And let's see the formulas here. That all right. So we need to go back a bit and discuss. But there is another way to both Q-learning and expected Sarsa are of policy algorithms, and essentially so expected the Q-learning is special case of expected Sarsa when our policy pi is a greedy policy, right? So we take just a maximizing action. In that case, the probability of all the non-greedy actions will be 0, and that makes the Q-learning just a special case of it can be viewed as a special case of expected Sarsa. And also we can remember that the ideas from expected Sarsa can be introduced to n-step bootstrapping in 2 different kind of ways. And one way was n-step bootstrapping, n-step expected Sarsa, but another way was n-step tree backup. And in n-step expected Sarsa, we were like taking the expected value only at the nth time step, but at tree backup, we were taking the expected value at each time step. So, and we can also produce a tree backup variant called TB Lambda for short, for the eligibility traces algorithm using tree backup. And again, here you can see this tree backup Lambda, backup diagram for tree backup Lambda. And also you can, let's go through this formula here. So for TB Lambda, we compute the Lambda return as a sum. So we take, obviously we take full reward, like for the current, for the closest transition, right? So transition at time step t. Then we discount by gamma this linear combination of the expected value of the next state, which given by V bar as defined before, plus we take this sum of our Q function evaluated for all action except the action that was actually taken. And we take that and divide it by the probability of action given by the policy. But for the actual actions that we take a sample, and in this case it would be not a sample but the all the Lambda return, right, for all the upcoming returns we will get from that particular state. And we also weight it by the probability of the actually taken action. And that would make another kind of linear combination here. You can think of it as, so again, we here, if we sum this multipliers here and this one, we will also get 1. All right, so that's total probability of all actions. Cool. And then we can rearrange this by kind of by expressing it as a difference between the lambda return for the like total lambda return multiplied by and we subtract the like Q value for this action and multiply it by lambda and this from here, and we multiplied the probability of that action. So that's just kind of equivalent forms of the same thing here. And then again, we can write down this approximation written in terms of TD errors. And here you can see that we have introduced the probability of an action as a multiplier in this sum. And you can kind of observe that if particular action that we've done was like a 0 probability, we will have this 0 here multiplied by 0, and then we again have this kind of reset of the impact of the trajectory that deviated from the on policy trajectory. But that will never be the case, because probably we will so the experiences are generated, or that will never be the case if we have on policy, right? Because always we have some non-zero probability. But if we act off policy, we can have this 0 here. Right, and again, the eligibility trace update is given here as follows, and you can see that this probability of action multiplier appears at the eligibility trace. All right, so this time the eligibility trace is weighted by the probability of an action. So rather than ratios of probability as we had with the importance sampling. So again, as you might remember, that all these algorithms are known to be unstable, but there are more stable variants of those. So there is a gradient TD and emphatic TD algorithms, and we discussed those in details when talking about this divergence problem as in off-policy TD learning, right? Or like in general off-policy learning with function approximation. Yeah, and there are adaptations of the GTD lambda, which uses like a true gradient. As you remember, it uses a gradient in projected Bellman error rather than this kind of semi-gradient. And we can produce, we can give the weight update rule as follows here. And we can also give this complementary vector update rule, and it will incorporate the eligibility traces. So you can see that both updates are incorporating the eligibility trace that corresponds to the Lambda, like eligibility trace Lambda learning algorithm. And here you can see that there is a GQ Lambda algorithm that is like a gradient TD algorithms, but adopted for action values rather than state values. And again, this is kind of similar, but this time we have this X bar, which is a sum over all actions weighted by the probabilities. And here you can see that we sum up the features. And so that is for, again, that is specific for the linear function approximation case. And you can see the TD error corresponding to the action here, given as in terms of this kind of expected feature vector, right? So you can think of it as expected feature vector. We kind of sum up all the features corresponding to state action pair by the policy probability.
What's the VT here?
Excuse me?
VT? What's the VT?
Oh, or VT? Okay, VT. So VT, as you remember in the this gradient TD, we needed to this kind of complementary vector that corresponds. Yes. We've used it to obtain the true like update corresponding to a true gradient, and that was done because we had this those three product of three expectations when producing the learning algorithm using this true gradient of projected Bellman error, we had three expectations, but we couldn't we cannot in general get the independent independent samples for all the components of expectation, because we kind of have the next state depends on the previous state, and all the samples are kind of correlated. So we decided that we can kind of iteratively update the component that corresponds to the two of the three expectations and sample only from one for our learning, right? So we like how our gradient descent algorithm works in general. So we take a sample and then use it to update. But if we we had this, so we can just quickly jump back to the derivation here. You can remember that we had this projected Bellman error. Then we had squared norm of projected Bellman error that we want to use as our learning objective. Then we have this algorithms or gradient of projected Bellman error. And you can see that we need so we have these three components here. for this gradient. And then we can express these components in terms of expectations. But we can only sample from sample one value of this three expectations. So here they are, all these three products in the brackets will become an expectation. And here X and is the feature like matrix, right? And the D is a diagonal matrix with probabilities of actions. And that's what we have from the experiences, right? And delta. So all those quantities come from the, from running our experiment. So we only have a sample of all these quantities. But for some of these quantities, we decide to compute the. Okay, so here is definition of you can see that it is the product of two of the expectations, and we deliberately decided to take this particular product for computational reasons, and this can be found by doing the least mean square update rule, and that allows us to iteratively define the exact update of the expectation of this product of expectations by incorporating this new observation at time step t. And then what we do, we just basically do the update in two steps. Update the v vector by doing this, computing this value, and then apply a gradient descent algorithm based on the sampled value here, right?
Mm-hmm.
Let's get back to where we left off here. So that's GTD, and here we just adopt those ideas to the eligibility traces case, and that will be that essentially, in brief, that results in a fact that we have this eligibility trace multiplier beside the both in the W update and also in V update.
Yep. So this was for the gradient TD algorithm, and there is a hybrid state value algorithm too that combines the uh, uh, gradient temporal difference lambda and the TD lambda 2.
Yeah, so here it is, and
Yeah.
you can kind of see that we have another beta, and I believe that's referred in some places as here in brackets it's written lambda and beta. I saw it in some paper recently, just when searching for some relevant materials.
It's I think the step size parameters, the alpha and the beta.
Yeah. So we have separate learning rates for V and W, right?
Yep.
Or yeah, so probably when we have this beta in brackets, it would be something completely different. So that would be some other beta. So this beta we had before. So for conventional GTD lambda, we have this beta as well. So no, so that's just our good old beta. All right. Yeah, so, but now we have this kind of two kinds of eligibility trace, right? So that where the hybrid is hidden, right? And you can see that one is updated using a multiply. So we multiply it by the importance sampling ratio, and another one is just as is. And then we just combine those two here, and here is in this, so this component has this difference of zt minus z some zb I don't know, and you can like imagine that when the important sampling ratio is 1, this factor becomes 0, and therefore we get just conventional TD algorithm, right?
They have alluded to in the text that it's the second set of weights, the v of t, and the second set of eligibility traces, the zt of b.
Yeah, so essentially we can kind of improve our algorithm further but we do introduce some extra computational cost to it, right?
Yeah.
And also finally we have this emphatic TD lambda algorithm that is just a modification of the emphatic TD discussed before, and this time you can see that we have this follow-on trace matrix F, and you can see that it is updated so now we kind of take this so this update is the same as we had before for M, right? And now we take M as a linear combination of the interest at time step t, and this follow-on trace. In this way, we kind of get the emphasis, but it is it has this eligibility trace incorporated in it through this F matrix, right? So by doing this linear combination of the two values, and then we get Z that uses like eligibility trace that uses emphasis, and then we just have the regular weight update as before, but the eligibility trace is different this time. This eligibility trace uses emphasis, and yeah, as you might remember, the emphasis will have like a larger value for the actions or for the updates that we believe for the states that we believe are of more interest for us, and it will be lower for the states that are of less interest, and that is governed by the importance sampling ratio, and the importance sampling ratio basically denotes how probable are those states under target policy. All right, and again, if we have the importance sampling ratio equal to 1 for all time steps, then this will reduce to the standard. So here it will become the conventional TD lambda. Or not become, but become similar. But in emphatic case, it's not quite equivalent. So here I believe in GTD lambda we had if we have this on policy algorithm, then we are equivalent to TD lambda, right? and in emphatic case, it's still a bit different. And yeah, so there are papers introducing all of these concepts, and many of those papers are authored by a research group led by the author of this book, Rich Sutton. So okay, and finally we get to this
Implementation issues, yeah.
Yeah, the implementation issues. And in this case, we can notice that this this can have a very high computational load when we have the eligibility trace that is non-zero at many positions, and we have a lot of parameters. For example, like when we're using artificial neural networks, right? And this can, but this can be resolved by observing the fact that usually we set lambda and gamma lower than 1, and almost always the eligibility trace for many states will be zero, nearly zero, and therefore we will have we can have this kind of sparse updates, and that will allow us to like make the computational complexity of all this stuff is like lower, and by doing like this implementational trick that we update only the few traces that are significantly greater than zero, and that basically allows us to use the eligibility traces for deep reinforcement learning. But yeah, so all we have here in this case is just this brief note, and probably when we proceed with reinforcement learning algorithms, and when we check out some practical implementations, we will see how this is done in practice. And from what I've heard so far, the reinforcement learning algorithms are like, there are a lot of engineering nuances you need to get right to make this work. And like, for example, many works from DeepMind, they have some hyperparameters that are set somehow, but they don't tell how did they find these values. And you need to run the algorithm is exact same hyperparameters to get good results, but that might be problem dependent. And sometimes when you fail to get good results with an algorithm, it might be attributed to this subtle difference in kind of engineering choices. And yeah, so that would be something really interesting to look at when dealing with more diverse problems. Okay, so the conclusion here, like to we have this figure in
I have reproduced this figure.
Oh, cool.
Nice.
So let me stop sharing and maybe we can have a look at the reproduced results from it, and maybe you can have like uh, mention the like runtime to produce this figure, how long it takes to run it, and you know, for different examples. And also it's interesting, why don't we have like, say, replacing traces for cartpole and accumulating traces for puddle world? So does it fail or what?
No, it for the random walk, the mountain car, the card pool, and the puddle world. Yeah, these are all represented by this figure here. Yeah, so this is the figure that I was talking about. This took approximately 2 hours to yeah, so to redraw. I think so. If we look from the book, the mountain car method, the accumulating traces and the replacing traces. Yeah, I've tried to fit as close as I can, but here in the accumulating traces, it's going up in the 0.4, 0.5, or 0.6 in the book, but mine is towards the uh, 0.9 or 1. So this is some uh, thing that I couldn't replace. The rest was the same. Accumulating traces was a part and whole at that. Yeah.
Okay. So have you tried to run the accumulating traces, for example, for puddle world?
Yep.
And what are so does it fail?
Yes.
Oh, all right. So, but and for cartpole, it kind of other way around, right? So the
Yep. Yep. Hmm.
yeah, that's uh, pretty interesting about that. And also, like, what other? I see that the numbers you have for mountain car are much lower than those in the book. So probably that can be attributed to some different settings, like I don't know, maybe they measure the performance for less episodes, or what is the
This
cause of that?
the mountain car example is taken from uh, this number of episodes. This was the original data, the lambda, and this is the method that we used. So I think so there must be some discrepancy between the way it has been initialized.
Mhm.
So yeah, so that might be one of the uh,
Yeah, I guess it's different. It might be different depending on like how many episodes you. So here, for example, in the book, the performance is really bad, and that number of steps per episode, you observe it like very early in the training, maybe first 20 steps, I guess, according to this runs I've done. Let me just quickly check it
yep.
here. All right, so it it for example, for true online Sarsa, it quickly drops the to 100 steps per episode, but for example, for the replacing traces, it's around 400 for the first 50 episodes, I guess, and it only slow. But again, that also depends on the learning rate you use, right? And
Yeah, you should share it. Let me try to stop my share there.
oh, okay. I'm just looking at this uh, graph here. So
Mhm.
here I have like 500 episodes, and so here is a number of episodes we done, and here is a step per episode, the y-axis, and it's logarithmic. So in the book they have the performance around 400 steps uh, per episode, right? So that would be somewhere around here, and that would probably make sense if you average the performance across first 50 episodes or something like that, right? So let me see the figure in the book. So yeah, it's higher than 400. So that would probably make it first 50 episode. And I'm wondering if in your experiments, how many episodes was done and averaged across to get the numbers.
It was more than 200. Uh,
Oh, okay.
well,
So
yeah.
that makes sense. Probably they just done less episodes, I guess.
Hmm. Probably, and the initial parameters that they might have used were a bit different.
Okay, but your parameters are like zero initialized or what? So the weights W.
No, they are not zero initialized. They are with the touch spaces and that is mountain car initialization environment. All the action spaces are -101. The position bounds is -1.2 to zero point 0.5. The speed bounds are -0.07 to zero point 0.07. And the terminal position limits is the same.
Yeah, maybe
Uh,
you can share again your screen so we can
yeah.
see. All right. So, oh, okay. So they are also using the implement the environment themselves. Uh,
Yep. This
okay.
is the environment that this guy has implemented himself. So that might be one of the reasons.
Yeah, but I believe that it's equivalent should be equivalent to that in uh, in gym for example, because that's
Mhm.
really a classic problem, like one of the very very basic ones. But yeah.
Anyways, but it makes sense. This makes sense if we look from uh, episodic point of view, or a bit of generalization. If we try to make these values go there, then this kind of like makes sense.
Yeah, cool. So that sums at least finally by this point in the book, we got to the tasks where we can like run some kind of simulation, and you can already imagine this applied to some or like a really simple robotics task. And even though this mountain car, for example, is really simple task, but it's like you need to do some to implement the control strategy using like classic control algorithms. You need to do some engineering work. You need to like embed this knowledge of the environment to produce this backward motion first and then forward motion. So there is like a really interesting strategy, right? So the reinforcement learning agent comes up with, for example, for the cart pole task, you can like knowing the physical properties of the cart pole, you can really produce the optimal controller that will work great. You know, there is no need for reinforcement learning for that kind of task. But that is because the task is quite straightforward. On the other hand, if you don't know the dynamics of the model, the like a lot of effort should go into the model identification to apply the classic control algorithms. But with the reinforcement learning, we just feed it the experiences, and it comes up with the result. So that's pretty cool.
In the end, this chapter has a huge conclusion and this one of the figures that we drew in the small mountain car, random walk, puddle world, and the carton pole is totally upon the uh, is totally drew in the conclusion part as well. So we have concluded by reproducing this figure and talking about this. And yeah, they conclude about talking about they can conclude talking about eligibility cases by the uh, the number of steps that are required to train, that is the computational part of it, and how cheap it is to uh, use some of the hacks that they have alluded to in the text, and how functional approximation might sometimes render that those hacks useless. So they talk about that too. And yeah, other than that, yeah, this is the end of this chapter.
So we have kind of this bias variance trade-off, right? By like between sorry, Monte Carlo and TD. So with TD we have more data efficiency, so less variance in our result because we bootstrap. But on the other hand, in function approximation case, we can have like non-zero bias, right? On the other hand, Monte Carlo are inherently unbiased, but also there might be a lot of variance, and we might need like a lot of experiments to come up with the good strategy. So that's, and the eligibility traces are looks like that is a way to try to get something from both of those.
It's kind of like on the midway between on the midway between Monte Carlo to the one-step TD methods. We can place it anywhere in that particular continuum, uh, as they are defined it here. They have alluded to here. By adjusting a lambda, we can place the eligibility trace methods anywhere along a continuum from the Monte Carlo to the one-step TD methods. Yeah.
Yeah, cool. So next week we will hopefully cover the gradient. So Mayank, do you have 2 or 1 week planned for the gradient policy gradient?
I think so. One to do it, there are 8, 9 headings. I suppose 8. There
Yeah, all
are
right.
8.
I hope we can do it in 1 week, because like a lot of concepts would be familiar for us in some way. So
Yes. Already browsing through it, reinforced with baselines and
yeah, and with that we will have covered all of the basics of reinforcement learning, essentially. And then we will proceed to the like more advanced topics, and maybe start to incorporate some of the deep reinforcement learning as well. And the knowledge of these basics will be definitely useful, but also I think that the introduction to deep reinforcement learning will enable us to deal with a wider variety of tasks efficiently. And also we will have a lot of engineering stuff to explore. And also there is this interesting list of reinforcement learning competitions Andrea shared on the Slack. And maybe there are also other tasks similar to flatland competition, and we can maybe do the overview and maybe select one that we find most interesting to explore. Flatland is an option, but there is also that NetHack, which seemed very really interesting to me. And so that would be fun to maybe get the coverage of popular tasks, and then to commit to one of those.
So we will try this next week. Please try to at least, I think so, I will say, uh, if you guys are interested in flatlands, please continue with the flatlands, or at least try to have one competition that you find some kind of interest in, so that we might also have some sort of diverse audience with respect to the number of competitions that they have, and we might distribute and constitute and share our findings with respect to the others when we meet here the next time. So that will be fun too.
Yeah, cool. Makes sense. All right. So see you
All right.
everyone next week. And thanks for joining.
Cheers. Thanks very much. Thanks for that. And I'll see you next week.
Thank you, guys. Cheers. See you next week.